So we want to now look at a harmonically trapped Bose gas. And our motivation is that this is typically what is realized in experiments. But the second point is also that we will see that G epsilon is different, even though that this system is in 3 dimensions. So that D is equal to 3, your G epsa has a different behavior as epsa to the power alpha, where alpha is equal to 3. For a free Bose gas, we knew that alpha was alpha was 1 by 2. But here we want to look at it. Now the Hamiltonian is p square over twice m plus half m omega square xi square plus half. So one can have an anisotropic harmonic potential, so that you have omega y square yi square plus half m omega z square zi square. The half factor should not be missed, but the energy levels are discrete, so that we have epsa x is nx plus half h bar omega x, epsa y is ny plus half h bar omega y, and epsa z is nz plus half h bar omega z. So that the total energy is now epsa x plus epsa y plus epsa z. We will ignore the ground state energy and try to figure out the total number of state, the total number of states G epsa that lies between 0 and epsilon. The idea is that once I know this number, then G epsa, the density of state, is given by dg d epsa. Further, we also consider particles which do not have internal degrees of freedom, so that we will set the factor G is equal to 1. If you do have particles which has internal degrees of freedom, then you need to multiply that factor. Now G epsa, capital G of epsilon, is then given by integral d epsa x, d epsa y, and d epsa z divided by h cube omega x. Not much of a space here, so 1 over h bar whole cube omega x, omega y, and omega z is equal to capital G of epsa. Here we have essentially is defined the variables, or defined a coordinate system, the variable h bar omega I and I, and this gives me the total density of total number of states between the energies 0 and epsilon. But one has to be careful about the integration limit. Clearly epsa z can go from epsa minus epsa x minus epsa y, and epsa y can be from 0 to epsa minus epsa x, and epsilon x will be from 0 to epsilon. Well, we want to carry forward this cumbersome factor that sits outside, but here we make the assumption that omega x equal to omega y is equal to omega z is equal to omega naught, so that I have h bar omega whole cube, and then the integral is 0 to epsilon d epsa x, 0 to epsa minus epsa x, d epsa y. If you carry out the integral over epsa z, you will be left out with epsa minus epsilon x minus epsilon y. 0 to epsilon minus epsilon x. The first integral, let's now carry out the integration over epsilon y, so that the first term is going to be epsilon minus epsilon x times epsilon y, 0 to epsilon minus epsilon x minus epsilon y squared by 2, and then I have an integral over epsilon x, 0 to epsilon. Outside I have a factor h naught omega whole cube, and this is your total number of energy states that is available between the energies 0 and epsilon. So 1 over h naught omega naught whole cube, 0 to epsilon d epsilon x. Substitute this part can simplify to epsilon minus epsilon x whole square minus epsilon x whole square divided by 2, so that I have epsilon minus epsilon x whole square by 2. So epsilon minus epsilon x whole square divided by 2, which is going to be half 1 over h naught omega 1 over h bar omega naught whole cube, 0 to epsilon minus epsilon x whole square d epsilon x. This integration is very easy to do. If you substitute epsilon minus epsilon x as u, then essentially you have 0 to epsilon u square du, which is going to be u cube over 3, 0 to epsilon, and that gives you epsilon cube over 3. So that the total number of energy states lying between 0 and epsilon is going to be 1 by 6 1 by h naught omega epsilon by h naught omega whole cube. So this has a very nice expression. The density of states is g epsilon, small g of epsilon, and that is which is of primary importance to us is dg d epsilon, which is going to be half epsilon square divided by h bar omega naught whole cube. We are going to work with this expression for the density of states. Why is it so important to us? Because I know that all the discrete sums over k I can replace by integration g epsilon d epsilon, and that is precisely what we plan to do. The starting point then is going to be the particle number. Well, one can also look at the canonical let's look at the grand canonical partition function, and the grand canonical partition function is given by minus sum over k ln 1 minus z e to the power minus beta epsilon k, which is going to be minus integral g epsilon d epsilon ln of 1 minus z e to the power minus beta epsilon. Now remember, we also have to separate out the ground state, that is the half h bar omega. So here one has to be careful, because the sum over k is now going to be replaced by the sum over n, where this set is essentially equivalent to n1x, n1y, n1z, then I have n2x, n2y, n2z, so on and so forth, right? But we will simply write down this and not separate out the ground state. Right now we will not worry about that. In fact, in the calculation that we want to do later on, we do not need this grand canonical partition function. We want to calculate the critical temperature first. The critical temperature For that, we need for the critical temperature for the Bose-Einstein condensate to appear in such a system. Now for that, I need the total particle number, and that total particle number is given by sum over n 1 over z inverse e to the power beta epsilon minus 1, and this is going to be integral g epsilon d epsilon 1 over z inverse e to the power beta epsilon minus 1. That we plug in the expression for g epsilon, which was half 1 over h bar omega naught whole cube times epsilon square. So I have a half factor 1 over h bar omega naught whole cube, and then I have integral of d epsilon square divided by z inverse e to the power beta epsilon minus 1. This integral, now I can substitute x is equal to beta epsilon, and if x is equal to beta epsilon, you see this means that I have 1 over h bar omega naught whole cube integration d of beta epsilon I have divided by beta, and I have beta epsilon whole square z inverse e to the power beta epsilon minus 1 divided by beta square, so that the expression takes a nice form omega naught whole cube integral 0 to infinity dx x square z inverse e to the power x minus 1, and this is kbt over h naught omega whole cube half of 0 to infinity dx x square z inverse e to the power x minus 1. But this form of the integral is very familiar to me, so I know that this is going to be kbt h bar omega naught whole cube f of 3 plus z, right? Now clearly, as you decrease the temperature, your z also changes. So you hit upon the limit where this function will have a limiting value of, if you recall, that fm plus of z is sum over k equal to 1 to infinity. I have z to the power k divided by k to the power m, and when I hit z to 1, I have fm plus 1 going to be sum over k equal to 1 to infinity 1 over k to the power m, which is zeta m, the Riemann zeta function. So this value of this function now goes and hits the upper bound, which is zeta of 3. So your the condition that the condensate starts to appear is given by n is going to be kbt h bar omega naught whole cube zeta times 3, and we put a subscript over here that denotes that this equation essentially gives me the critical temperature at which the condensate starts to appear. So essentially it is at this temperature you have the particles starting to populate the k equal to 0 momentum state. The ground, sorry, not the k equal to 0, but the ground state of the system, because it's no longer a free particle system. One has to keep that in mind. Therefore, using our analysis that we did for the free particle gas, we know that in the excited states, if I just look at this fraction n epsilon divided by n, the total number of particle, this is going to be 1 for T greater than Tc. So once again, then when you have high temperatures, you will have kBT over H bar omega naught whole cube F3 plus Z. In this case, you will have this equation that is valid, and you have to determine the fugacity from this relation, and that effectively tells you that Z is to the lowest order. I know that F3 plus Z is going to be Z to the lowest order, so that Z is going to be N times H bar omega kB T whole cube. This is going to be to the lowest order. For T less than Tc, I have F3 plus Z being substituted by zeta of 3, so that you have an epsilon for T less than Tc. One can do the very simple calculation. We will do it on the side and plug it in there. N epsilon over N is going to be, I have kBT over H bar omega naught whole cube zeta of 3 divided by N. And if you see that this quantity is going to be, using this relation, I have zeta 3. If I use this relation over here, I write down essentially zeta 3 divided by N, 1 by H bar omega naught whole cube is going to be 1 over kBTc whole cube, so that this expression becomes T over Tc whole cube. Remarkably, you see this factor has now changed. For an ideal Bose gas, this factor was T by Tc raised to the power 3 half, but this is now T by Tc raised to the power 3, and this factor solely depends on the density of states. When we basically intuitively said that why does a specific heat of an ideal Bose gas near zero temperature scales as T to the power 3 by 2, we said that, look, I can excite particles for finite temperatures, I can excite them, and they are at most going to get energy levels, go to energy levels with the momentum values, which is Km, determined by H bar square Km square over twice M is equal to kBT. However, it should all, and then we said that the total energy was volume times Km raised to the power D by 2, Km raised to the power D times kBT, because each of these particles carry in thermal energy kBT. But this Km raised to the power D follows from the density of states. So even though you can still be in 3 dimension, but as we are seeing in this example, my value of D, the exponent that comes in, is clearly different. It's no longer 3 by 2, but it is 3, and that is solely the property of density of states. That you should keep in mind. For temperature, for the ground state, N0 over N is going to be 0 for T greater than Tc, and it follows from this expression is going to be 1 minus T over Tc whole cube for T less than Tc. So one can of course plot this now. So as we did for the free particle case, we can plot this fraction of N epsilon over N and N0 over N as a function of temperature. So this is my unity and this is my Tc. So I know that for T greater than Tc, my ratio of N epsilon over N is unity, so this remains like this. And as I cross the critical temperature, this expression follows T over Tc let's write it here, T over Tc whole cube. In contrast, the fraction n0 over n, the number of particles populating the ground state, is 0 for all temperatures below Tc, because you can accommodate these particles in the excited states, and as you keep on reducing the temperature closer to below Tc, then essentially you start populating the ground state more and more, so that at T equal to 0, this ratio is 1. And therefore, you have a nice plot that goes, so this is, let's do it a little bit more carefully. That goes like this, and this is 1 minus T over Tc raised to the power